No, so I didn't have enough for everyone. Okay, so I apologise for not printing enough based on my previous experience. But the electronic version is on the website, so feel free to share for the moment. Today's lecture is my last one with you until next semester, and it's about calculating sample sizes. And that bit shouldn't take very long, and after that I may go back to the end of the previous one and talk about some more about those specific stats procedures. Okay, so the first piece of information I need to tell you that is the most important thing to know about sample sizes, that everyone should know, but many people don't, is that you cannot calculate a sample size unless you know how you're going to analyse your data. So what happens is that people come to me or to a statistician and say, hey, I've got this idea for some research. What sample size do I need? You can't answer that question until you decide whether you're going to use a t-test or a chi-squared test or an overall what. Until you've made that decision, you can't calculate the sample size that you need. Because the whole point of needing a certain sample size is that certain statistical procedures work better with more or less amounts of data. So that's the most important message I could possibly send. So you can't just off the cuff say, yes, I need 400. All right. Cool. So that's if I've said that, I've said enough. But what I'm going to say is there's 5 things that affect sample size if you're going to use statistical methods. 5 things that affect sample size, and each of them affects it in a different way. And so from a general point of view, you can have an expectation of needing more or less participants in your research based on these things. And then there are a couple of calculations which give a more precise number. That's approximately how many you'll need in order to achieve significance if there really is a relationship there. And that's what this handout here is about. Now this lecture is a bit old school, there's no PowerPoint, and there's no Prezi, it's all in the handout. So I'm just going to run through it. So let's see. There are 5 things, and the 5 things, I'm just going to write them all together, are which test. It just works better if I do it live, right? So which test, the size of the difference you want to see, or effect that you're looking for, how variable the results are, that's 3 things. The significance level, and the power. These are the things that you need to know in order to calculate the sample size, all 5. And they are the things that affect the sample size even if you sort of only have a general idea of what they are. So when you look at someone else's research and you think about whether you have the answers to all of those questions, it should give you a general idea of whether they need more or less. And when you're doing your own, you can, once you have all this information, you can calculate a sample size usually. Personally, I don't know how to do all of them, but I can do some of them. So I'm going to talk about these things. So you need to be able to choose which test. If this is a hypothesis testing situation, you need to choose which test you're going to use. And the way to do that is what I did a couple of lectures ago, where you think about the types of variables that are involved and how they're going to be related to each other, and whether you've got repeated measures or independent groups. And those bits of information allow you to decide which test you need to use. So maybe it's a paired t-test, maybe it's an unpaired t-test, maybe it's a chi-squared test, maybe it's ANOVA, maybe it's logistic regression. Once you've made that decision, then you can start to decide on the sample size. And there are 2 bits of information about which test. One of them is whether it's based on categorical and numerical outcomes. And the other one is whether it uses repeated measures or independent groups. So it's really 6 things that you need to know. So, in general, things that need categorical outcomes, things that use categorical outcomes, require more data. Categorical outcomes, bad pencil. Green. That's better. Numerical outcomes require less data than categorical outcomes. And the reason for that is that numerical outcomes give you more finely grained information, and so it's easier to tell when things are different when you have numerical outcomes. Repeated measures require less data than independent groups. And the reason is it's to do with the variability. So if you have the same repeated measurements on the same person, you're comparing that person to themselves. But if you have 2 completely separate groups, you're really comparing, in a way, the whole group to the other whole group. And so it's less finely detailed information and therefore requires more data to do it. All right. The next thing is the size of the difference or the effect that you're looking for. I'm going to draw some pictures for that. So this is where my jittered scatter plot comes in. So, suppose I had 2 groups that were like this, and 2 groups that were like this, and this one has a mean here and a mean here, and this one has a mean here and a mean here. It's easier to tell that these 2 are different than it is to tell that these 2 are different, because the difference between them is bigger. It's easier to see bigger differences. And statistics is able to perceive those bigger differences as well. So the bigger the difference is that is really there, the easier it is to find it. So here's the thing. In actual research, like not from a statistical point of view, but from a medical point of view, some differences just don't matter. So, you know, if I wanted to know about the difference in temperature before and after chili, a difference of 0.01 degrees Celsius really doesn't matter that much, okay? You know, really I'd be most interested in if it made a difference between, say, I don't know, 37 and 40, because in a child that would make a big difference, right? So 3 degrees would be huge, 1 degree would be pretty big. There would come a point where you go, look, if it's that size difference, I just don't care. And the statistics will tell you that there really is a difference, regardless of how big that difference is, if you have enough data. So if I have enough people so that they've got a nice little cluster just here, the fact that these are not very far apart becomes less relevant because I've got more data to be able to see. And so the statistics will come out and your unpaired t-test will give you a p-value of 0.01 and you go, yes, there's a significant difference. But you might not care. They're totally different. Yes, it definitely makes a difference, but the difference is only like this big. So I don't care anyway. That's the difference between what they call statistical significance and clinical significance. Clinical significance is not a statistics question. It's you as a practitioner thinking, how much a difference do I actually care about? And I can't answer that question. Only you can, or people who have been in the area of the research a long time can answer that question. And usually you can sort of get that and glean it from other people's research where they declare that something's a big difference and you can look at it and say, well, they seem to think that this difference is big, is important, and so maybe I should too. But the bigger that difference that you would like to see, that first difference that you think is, worth caring about, that's the difference that you want to think about. Well, if I get anything less than that, I don't care. Anything bigger than that, I need to be able to find it. And if it's too small a difference, I'm not going to be able to see it without more data. So small differences require more data, and big differences don't require so much data. Okay, right. The variability of the results. You see in this one, look at this. These are quite variable. Individual people can be a long way from their mean. But the more variable that gets, the harder it is to tell the difference. So if the difference was only small, but everyone was really close to the mean, I would still be able to tell that those two groups were different from each other. So because the people are less variable, I can still see that difference even though it's a small difference. So what happens is it's not so much that these two things separately are important, it's that together they're important. You really just want the difference that you would like to observe to be in some sense smaller than the variability overall. So you don't want the variability to sort of outstrip how big the difference is, otherwise you won't be able to see the difference. But if things are very not very variable, you'll be able to detect a small difference. So you only really care about how big these are relative to each other, and I will do a calculation in a minute to illustrate that. However, if things are highly variable, then that's going to make it tricky to find differences without lots and lots of individuals in the study. I should say that in a completely technical sense, you don't actually care about the variability that the individual people display. You only care about the variability that a group of participants as a group display. So you're interested in how different groups might be different to each other as opposed to how individuals are different to each other. Now, if individuals are very variable, then groups will be very variable too. But if individuals, the bigger your group is, the less variability there is between groups. So I'll get to that when I talk about the chi-squared test as well. Actually, it's on the paper there. When you do the chi-squared test, each person is having a yes or no outcome usually, and variability in that, well, what does that even mean? What does it mean to be variable? Some people say yes, some people say no. The question is, if I have a group of, say, 10 people, well, how variable is the percentage of them that say yes? If something's really, really rare, if you've got 10 people, then most of the time you'll have none of them or one of them, right? Most of the time. And that's not very variable. If you have something that happens half the time, and you've got 10 people, you'd expect about 5 of them to say yes and 5 of them to say no, but it would be pretty likely to have 6 say yes and 4 say no, or 3 say yes and 7 say no, because that could totally happen if you just randomly pick 10 people. So out of the group of 10, a group of 10 is more variable when something's sort of 50% than it is when it's really, really rare or really, really common. So what happens is if you have a percentage, if you're looking at a yes-no outcome, if that yes-no outcome is really, really, really common, like 90%, you don't need so much people to tell the difference. You just have to have enough to make sure you're going to get at least one person in the category you want. Okay? Talk about them more in a minute. The last two are actually pretty good because they're normally fixed for you. Significance level is that 5% cutoff. Okay, you say that when you're at 5%, if my p-value comes out below 5%, then I will declare that it is a significant result. And that's what you're going for when you do statistics. You want the difference that you are looking for to come out as statistically significant, because that's the whole point of statistics, to find things. But the lower you set that p-value cutoff, the lower you set that significance level cutoff, the harder it's going to be to achieve. If you want to get below 5%, it's going to be much easier to do that than to get below 1%. And so if you want to get below a certain level, you're going to get below a lower level of more significant is a lower p-value. So if you want to get an even lower p-value, you're going to need even more people. Right. And the final thing is power. Power, mathematically, is the chances of finding a result if it's really there. So if there really is a difference, how likely is it for you to actually observe that difference in your statistics? Okay, I'm going to draw a picture for that. Actually, it's this picture here. It's these people here. There really is a difference between those two groups. This group really is, on average, higher than this group. But if I randomly happen to pick a sample of these people and I picked this group and this group, then those two groups are roughly the same. And my statistics would say there is no difference. So that's a type 2 error. There really is a difference, but I didn't find one because I happened to pick groups out of the bigger groups that were similar to each other. I hate that they numbered them. I wish they'd given them better names, but there you go. Power is about the chances of that not happening. So I might have a 20% chance of accidentally picking two groups that were similar, even though the bigger groups aren't. And power is the chances of that not happening, so 80%. That's the idea behind it. Of course, significance level is the other way around. My two groups are more or less identical to each other, and I just happen to pick ones that are different today. I pick these ones, and I go, oh, look, they're different, because that's my graph that I'm drawing. I go, oh, wow, look how different they are. And I would come up with a difference even though the big groups aren't different to each other. That's type 1 error. So I'm just going to write that on there just so you know. It is on the other side, I just don't know if I actually drew a picture of it. I'm sorry. It's here. Type 1 and type 2. Okay. So, if you want it to be really likely to come up with a difference, if it really is there, you're going to need a lot more people, because it's really rare to be far away from the edge. So the more people there are, the less likely it is to pick people that are on those extreme ends so that they overlap. Most people choose a power of 80%. Now that seems pretty low, only having an 80% chance of finding a difference, even if it's really there. But in practice, it's really difficult to guarantee in advance a higher level of power than that. Like if you needed 100% power, then you would have to have everybody possible in your sample, like doing the census of the Australian population. Okay, so, and even that doesn't count, because in medicine you're actually interested in people who probably don't even exist yet, especially if you're working on children. Okay, so it's impossible to get 100% power, and the higher percentage power you get, the harder it is to achieve in advance. Like you might find a difference and that's fine, because then there it was. Significance level is traditionally set at 5%. So most people just stick with these numbers and run with it, because you've got to use something to calculate your sample size. Good-o. Right, there you go. These are the things that affect it. So if I saw that someone had done a chi-squared test and they were looking for a difference between the chances of yes and no of maybe 1%, and then I would look at it and go, well, and the probability of it actually happening is maybe about 50%. I go, well, 50% is where it's most variable, so I'm going to need quite a lot because of that. I'm looking for a really small difference, I'm going to need even more, and I'm using a chi-squared test, which means I'm going to need even more because it's a categorical situation. So that sort of situation, chi-squared test, when the chances of getting yes is about 50%, and you're looking for a small difference, needs the most, and it's like in the hundreds, thousands even. Whereas if I did a t-test, I would need less. And if I did a paired t-test, I would need even less. And if I did a paired t-test on, say, especially genetically pure mice, who are all very similar to each other, so there's a very low amount of variability, I would need even less again. So that's the sort of context that you're thinking. All right. But we can do some actual calculations for some of them, which is what I want to go do now. So what I'm going to do is I'm going to just put this on the screen for the moment and point out to you that there's this, Russ Length has a comprehensive suite of online calculators if you want to look them up. They can be quite difficult to understand. There are plenty of other online sample size calculators out there, and they'll ask you to chuck in various things. What I want to point out to you is they will almost always ask you to specify the 5 bits of information that I have put in. Okay, they will ask you you'll choose which hypothesis test you're interested in from a menu, and then you'll put in some sort of measure of the difference you're looking for. You'll put in some sort of measure of variability, usually a standard deviation or a percentage, and you'll put in a significance level and a level of power. It'll ask you for 5 things, and then you'll be able to get your sample size out. And a lot of them will have sliders, and you can change the power level and it'll change the sample size level. I'll show you one of them actually. while I'm thinking about it. Will it work? Fingers crossed. Of course not. Of course it doesn't. Yeah, that's all right. Right, this is my first link on Google. Wow, what does that even mean? This is for confidence intervals. Okay. Oh, which I haven't covered. Damn. At least you can see how I go about trying to find information. Oh, interesting. Simple randoms. This one's only for estimating proportions. My goodness, people. No, SurveyMonkey's no good because that's proportions, isn't it? All right, just a second. Sample size calculator, t-test. T-testy. Here we go. What this one asks me for is a value for what I think the mean in the first group might be, what I think the mean in the second group might be. That's how I figure out the difference between them. A value for sigma, so the standard deviation, that's the variability. I put in whether it's one-sided or two-sided. You should always do two-sided because it's more conservative. You enter a value for alpha, which is the significance level, a value for power, which is the power, and look, it's already put in 0.05 and 0.80, like 5% and 80%. They're the standard values. And then it will tell you the sample size. So if I thought the mean in one group was 10, and the mean in the other group was 15, and the sample size was, say, 2, not sample size, the standard deviation was, say, 2, it would calculate it and it would tell me, yeah, 3. No one will believe you if you say 3. Anything under 10 is a bit ridiculous. Calculate. 16, okay? So there you go, it's a sample size calculator. It should actually be possible to put in other things and actually to put in the sample size you've got and calculate the power instead. But that's how a lot of them work. They ask you for various bits of information. Okay, back to the document camera. Now, Medical Statistics at a Glance by Aviva Petrie and Carolyn Sabin, of which there are about 6 copies in the library and 1 in the Maths Learning Centre. Yep.
So when you said the mean for one group and the mean for the next group, what do you mean by that? In your sort of like hypothetical.
I've got an example here. You don't actually need to, well, let me just talk about that. So in my hypothetical one here, when I say the mean for one group, I mean the average in that group that I would be expecting to get, and the average I would be expecting to get in the other group. Now, normally you don't really know what you're expecting because if you knew that, you wouldn't have to do research. What you know is what it would be just for the general population. So in a lot of research, for example, in researching a new drug that's affecting, say, some measure of the concentration of some hormone in the blood, you would know normally for most normal people what that concentration would be on an ordinary day, and that would be the average in your placebo group. And you would know, and you would think, well, I'm only going to be interested if it changes by about 5 micrograms per milliliter or something. And then you know that the other, so you might know it'd be 10 here and the other one would have to be 5. So yeah, some sample size calculators online just ask you to put in the difference between them rather than the actual 2 individual values, which is what this calculation is based on. So this one's taken out of Medical Statistics at a Glance. It's called Lair's formula, and if you ever use it, then I would reference Medical Statistics at a Glance. If you actually look up the book, you can find the original reference, and you can look even more sophisticated if you reference that. But I usually say, based on Lair's formula, as reported in Medical Statistics at a Glance. Okay, you do not usually in a research proposal or a paper have to actually provide the actual calculation. You just have to say, we did a sample size calculation based on name of formula, and this is the answer we got. But normally what you do have to do is specify the 5 things that went into it. So in this one, these are the formulas here. There's one for the unpaired t-test, there's one for the paired t-test, there's one for the chi-squared test. Anything other than that, we'll need to sort of look it up together and try and find something a bit more specific than that. So I've got some examples of how that works, and I'm going to do them live. You have my handwritten version there already. You can see how it's going to be built up. So in the first one, it says, suppose the difference where this, I'm going to pretend I'm doing my chili experiment. I'm going to look for a whole degree Celsius different. Now that seems a bit unreasonable, but it's easier for me to use the number 1. So what if the standard deviation of people's temperatures is a whole degree? You know, on average, if I sort of went 37 degrees and went up a degree and down a degree, I'd cover like 2/3 of people. Now that's probably a bit wide for how standard variable people's temperatures actually are, but it's just an example to give you an idea of how it's going. So there's this thing called the standardized difference as opposed to the standard deviation. The standardized difference in the book, it's called capital D in Medical Statistics at a Glance, and I calculate it for a t-test by doing the difference I'm looking for divided by the standard deviation. So I'm going to do this live now. The standardized difference is the difference I'm looking for divided by the standard deviation. Now this standard deviation, you're thinking, well, if I haven't collected any data yet, how do I know what that is? Well, you get it from the last person who published something about this. So you go and look up in a paper, and the paper says, we did a study on temperature, and on average, in our sample, the standard deviation came out to be 1. And so you use the one from the previous person's paper. Okay, so that's the only way to know. If no one has ever done research on this before, there are ways of dealing with that, and we can talk about them in person. So I've got 1 for this and 1 for this, and it comes out to 1 when I divide them. Sweet. And then the sample size normally people call the sample size n is 16 divided by d squared. So 16 divided by 1 squared is 1, is 16. And that's always per group. Ooh, now where did this 16 come from, we're wondering? Well, when you want to do a really, really accurate what is that number? Oh, that's a D. Right. When you want to do a really, really accurate sample size calculation, you have to use the probability distribution function of the normal distribution, or at least the t distribution. And there's all these calculations that go together into that. And what Lair did when he created this formula is he said, well, if you were using 5% significance, and if you were using 80% power, you'd get these numbers in that formula. And when I figure out the top line of my calculation, it comes to 16, basically. Or at least, I don't know, 15.98 something. And so he rounded it off to make it easy for us. So that's where the 16 came from. If you wanted 5% significance and 90% power, you would use the number 21, just because that's the number it comes out to be. The whole point of this is so that you don't have to go to great lengths to figure out a rough idea of how big the sample size needs to be. Okay, what if instead the difference I was looking for was still 1 degree Celsius, but the standard deviation was half the size? What if the difference I was looking for was still 1, but the standard deviation was 0.5? Well, let's see. The standardized difference would be 1 divided by 0.5, which would come out to 2. And so the sample size would come out to 16 divided by 2 squared, which is the same as 16 divided by 4, which is 4 per group, which is pushing the limits of believability. If I have 4 people, I mean, how do I know that they're just not randomly hot people? So, whatever. But that's the idea. And what I wanted to point out is that if the difference you're looking for is bigger than the sample size, that's going to need not very many people. Not sample size, crap. Bigger than the standard deviation, you're going to need more people. If the difference you're looking for is smaller than the standard deviation, it's going to get really bad. Look what happens here. I'm not going to do the calculation for you. What if the standard deviation was 2 and the difference I was looking for was 1? Now the difference I'm looking for is smaller than the standard deviation, and I get 64 per group. If you halve the size relative to one of the difference relative to the standard deviation, you're going to have to have 4 times as many people. That's basically what it says. If you double, if your difference you're looking for is half the sample size, you'll need 4 times as many people. If it's a quarter the sample size, you'll need 16 times as many people, and it'll just get worse and worse. So you do want to try and, it'd be very lucky for you if you're looking for a difference that's close to 1 standard deviation. Now, if you don't know what the standard deviation is, you can always say, we can find a difference of 1 standard deviation's worth with 16. So I know that I can find the difference of the same size as whatever the standard deviation is with 16 per group. And so normally you'd say that as, we can detect at 5% significance and 80% power a difference of 1 standard deviation in the outcome using 16 per group. You just leave it at that. Not even worry about what the size you're looking for or the standard deviation is, and just report that. What some people call that is Cohen's d, C-O-H-E-N. So this standardized difference here is also known as Cohen's d. C-O-H-E-N. Just so you know. Cohen has this sliding scale. Many statisticians don't believe in it. They call it t-shirt sizes, where he says that a Cohen's d of 0.4 is of 0.2 is small, and a Cohen's d of 0.4 is medium, and a Cohen's d of 1 is large. They call it t-shirt size, sample size calculations. You can look that up. If you look up Cohen's d sizes, you'll see the sliding scale. Chi-square test is a whole different matter, because the chi-square test is not based on means and standard deviations. You don't have numbers that you can do averages and standard deviations on. You don't. So you have to find a different way of dealing with it. So in the chi-square test, you've got a yes or no outcome, and we need a number to describe the whole group. So the mean describes the whole group for a numerical outcome, while a percentage describes the whole group, or a proportion describes the whole group for a yes-no outcome. So the D will be the difference in proportions or percentages, and the P will be the percentage or proportion that I'm looking for. So over here, so suppose I wanted to see in one group, I wanted to see a difference of 3 percentage points from the other group. So maybe one group is 20% yes, and the other group's 23% yes. And what if I thought that on average it was going to be about 20%? Okay, so maybe in the grand population, 20% of people have this condition, and I want to see if I can make a difference to that, and so I want to get it down to 17% in my treatment group. That's the idea behind it. Okay, so you can either leave them as percentages, or you can turn them into proportions. Statisticians, for some reason, despite the fact of talking about power as a percentage, for some reason, when they talk about percentages, they want to write them as decimals. I don't know why. It's just something that they do. When they talk about power, they talk about 80% power. When they talk about actual percentages, they do them as decimals. I don't know why. So we'll calculate this. like that. So P is 20%, and 1 minus P is the other 80%, and I'll times those two things together. And when I calculate that in my, here's one I prepared earlier, it comes out as 0.4 today. Lucky that I chose 20%, or it would have come out to some horrifying decimal. I would have had to round it off, which would have been fine, because it's, sample size calculations are all approximate anyway, so rounding it off doesn't really matter. And then the standardized difference is the difference that I was looking for divided by this square rooty thing. And that comes at 0.075. So the sample size will be 16 divided by d squared, which in this case comes out as 2,843 per group. Sweet. It's really hard to find differences that are small when you're doing percentages. So usually if you're looking for differences in percentages, you want to look for a bigger difference than 3%. You want to go like 5% or 10%. Because if you think about it, well, if you've got 100 people and 3%, that's only 3 people who are getting a benefit from this out of 100. So you might want to get a bigger percentage difference that you're looking for. There are more accurate versions of the chi-squared one if you look them up, but they will tend to give you numbers in the hundreds. That's just the way it is. But if the chi-squared test is all you've got, then that's the best you've got. Some research that is on very rare forms of cancer, you won't do sample size calculations. You'll just say, we're going to get as many of them as we can. And that's the best you can do. Of course, if you've got doing it on rats and you're implanting the cancers, then whatever, you can do the proper calculation and say, we need 20 of them, send them down. But with animal things, ethically, you have to show that you've done a calculation so that you can prove that you really do need those animals. With people, well, it's even worse. So, and you've got cadavers, and you really want to make sure that if you don't need more than that. So one of the ways of dealing with that is to do matched pairs sort of situations. Now, I don't have a calculation for McNemar's test, which is the paired situation, but I have a feeling that you would just quarter the sample size like you do with the paired t-test. Okay, there you go. There's some calculations. I just wanted to show you how they're done. You can attempt them yourself. Feel free to visit the Maths Learning Centre and have, well, email first, because if you come on, say, Monday when the assignments are due, you're not going to get much of a look in. But feel free to contact me and talk to me more, or just send me an email and say, I did this calculation, does that seem right? I'm okay with that as well. If you're just not sure, some of these things are the sorts of things that's just best to talk to someone about. Yeah. Any questions on sample size of any kind, even if it's something I've already said and you just want me to clarify? Cool. So I will say to you, when you hand in your, you have a formative version of your research proposal, don't you? You don't have to do sample size at that stage. You can if you want to, and then it'll get it out of the way. But don't stress too much about it until later if you don't want to. But yeah, you don't have to put it in there, no matter what your supervisor says. But in general, you should try and keep your supervisor happy. It's always a good plan. But yes, if they try and suggest to you that you can, without having decided what the statistical procedure is, that you can do the sample size without knowing that, then you can say, actually, David, our statistics lecturer, says that's not possible. Can we hold off for a month or two until we've made the decision? And be very polite. I'm going to be very polite to supervisors, but you can at least, reference a higher power, and feel free to give them my email address if they want to take it up with me. So, I'm serious about that. The more I can tell people that you can't do sample size before you've chosen the statistical procedure, the better the world will be. All right, cool. Look, I think that's enough. When I come back next semester, I will talk about any statistical thing you want to ask about that more than you will be interested in. If only one person asks a question, then you get to do the one that you're just interested in. You all have a space on your critical appraisal to say what statistics appears in your paper. The main purpose of that I asked them to put that in so that I could look at your proposal of your critical appraisal thing and know the list of statistical things that I should cover next semester. So the only reason to put that in is to have me talk about those things. So if there's something in there that you really want me to talk about, make sure you write it in that box, because I'll be more likely to talk about it then. So I'm not trying to get you to know what all those things mean. The whole purpose of writing that is that you don't know what they mean and I can explain it to you. So don't stress about that, just stick in whatever you want. If there's not enough room, it's like a word thing, so you can make that box bigger? Kerr says. If there's not enough room, just make the font size smaller in that box. I'll tell them that you can do that just for that box, okay? All right. Thank you very much. If you want to talk to me, email me, and I'll do the best I can to fit you in sometime. Thanks very much.